we left something yesterday I think ought to clean up a little bit, and that's a sailboat.
Yeah.
Can we talk a few minutes about the sailboat, gang? And the idea about the pressure, the force being perpendicular. If this is the side of a swimming pool, and I have some water in there, turns out, let's take this point right here. At that point, water's pushing with a force in all directions. It's pushing like that, it's pushing like that, on this point, and every other point also. And it's easy to see why we say that the force of a fluid against a surface is perpendicular, because all of those would all have components that would cancel out vertically and would be left with a force like this due to all those. So that we can see, can't we? So we have a little rule. When the water touches the surface, the force of the water against the surface will be perpendicular. And we can see why. All these would be the resultant of that. But we talked about something different yesterday. We talked about wind, a fluid that's moving. And let's suppose a fluid that's moving hits the surface. Let's suppose we have a surface like this. And the wind comes in and maybe, whoom, air molecules bounce against that surface. Well, if the air molecules then, if they bounce against that surface, we might tend to think that there would be a force against the surface like this. Well, if there were, that force would have a component like this and a component like that. Is that true? And those components are real. Now, if this is a smooth surface, you can't have a component of force like this unless the surface will give you a component of force back. And a smooth surface can't do that. So if it's perfectly smooth, this component cannot exist. If I'm on the ice and I have icy shoes and I start walking, I can't move because I can't exert a force against the ice because the ice can't exert the reaction force against me. Forces occur in pairs. So on a perfectly smooth surface, it turns out the force of impact will be perpendicular to the surface. You could also look at it with momentum, which we'll be talking about in a little bit too. Let's suppose, for example, suppose we have a momentum vector here coming in, an mv vector. All right, that mv vector would have a component like this and a component like this. If the wind bounces off like this, then bouncing off, we'd have a momentum vector like this and a momentum vector like this, the same. So it turns out in a y direction, we've got as much momentum before impact as after. In our x direction, this would have to move with a momentum, let's suppose these are coins or sailboat, twice the momentum vector of this. So now this minus this is the same thing as this. Put numbers in, put this 1, put this minus 1. How big is the momentum vector? 2. How about components this way? Satisfied, because we got maybe what's this, 0.8 before? What do we get afterwards? 0.8, leaving nothing for sideways. So from the conservation of momentum, molecule come down, boom, hit something. That something will move off with twice the momentum of this component as it has to begin with. You can do this with coins. You can do this with balls. You might have a ball here. Pool ball comes down, hits, bounces off over here. What's the direction of this ball? Right along there. And my momentum of the ball this way and this way is the same before and after. And my momentum this way plus this way is the same before as after. So I got to have a +2. The old bit about when you bounce off, you give the other object more momentum than either of these had. You've done that in the lab. Well, here's an example of that right here. I like billiard ball physics as much as I can look at mechanics in terms of balls hitting each other. That I can picture in my mind. And I'll have a lot to say about that when we talk about heat and temperature and things like that. Billiard ball physics. That's the way to go, at least for me. And then on these sailboats, again, let's look at it. If I have a sail like that, and if I have wind coming anywhere from this side, here, 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 I'll have a force, and let's just take it the middle. That's in that direction where I have 90 degrees here. So anywhere up here will give a force in that direction. Now we're going to take that force and bust it into components. What components? We'll take the component along the keel of the boat, because that's the component of interest. The other ones have no interest and maybe has to be compensated by leaning or whatever. So where would you like your boat? We can put the boat in any number of places. Let's put the boat, for simplicity, like that, in that direction. Now we want a component along that direction. So there's where people get mixed up. They get this part and they don't know how to do this. Well, that's what we want. And then we have the other component. Now we bust it up and we say, aha, that boat will have a force in the direction of motion, so the boat will go. Now, where's the wind coming from? Who cares? As long as it's coming somewhere from over here. If the wind's coming from here, then the sail will bulge the other way, and in our drawing we put it the other way and our boat would go backward. So you could say the wind is coming down like this, bouncing off, or you could say it's coming like this and bouncing off. The sail doesn't care, except that as you gain speed, let's suppose you have a wind that's coming in like this. As you go faster and faster and faster, pretty soon your wind is coming right along your sail. Then you've had it. So you get into a relative velocity thing. If you're familiar with the first edition of my textbook, or the second edition even, at the appendix I put this, and I went through a whole thing about relative velocity, because it occurred to me that, wait a minute, gee whiz, why can't you go to the speed of light? You say, well, that's because of the friction. All right, how about an ice boat? With ice runners, we have very, very low friction. My gosh, you should be able to go to supersonic speeds. And I was troubled by that. I had to kind of figure it out. Oh, no. The faster you go, the wind starts to change direction. So you get into a relative wind thing. Then you get into velocity vectors, and I dropped it in the third edition after that because it's complex. But it's called information overload. Did you guys experience information overload in your education? Boy, I did. Just too much, too fast. So you got to kind of nip it down. So, all set? Okay, gang, let's talk about momentum. Momentum. We've talked before about and we've talked about and your student asks, well, which is it? Is it this or is it this? And you say, check your neighbor. And then someone says, you can't have it both ways. And you check your neighbor, and your neighbor says, if you do it right, you can always have it both ways, right? That's my credo. Okay. Well, it turns out this is what acceleration is. That's what it is. And here's how you get it. And it turns out the quantities will be identical. So this isn't this. It's just that the quantity of this equals the quantity of that. And I think at this point we can start to get away from this. And so we can say like this. With my non-majors, I introduced the delta sign about here. It's a matter of taste, a matter of style. We all have different styles. I just forego it. I don't put it in when the kinematics equations, because the kinematic equations are the most difficult looking equations in the whole course. They're not necessarily the most difficult, but they look more difficult. And when you put this stuff in there, it's my experience with my non-majors, it's intimidating. And I don't want to spend my time teaching math. And it would be nice if I had the luxury of having a math teacher in concert with my teaching where we could do it together. That's the ideal thing. Because there's so much of physics. Teaching is involved with math, how to draw graphs. I mean, velocity, acceleration, displacement. We usually talk about, let's draw a graph so we can make that clearer. Well, that's my contention for the non-major. The graph itself is more complicated than the concept. So you're not simplifying it. But for the major, if you have someone in your math class doing that, then I think you're way ahead of the game. The tools of physics and physics. Hey, gang, There's a difference between the tools and the physics. It's like my friend wanted to take a course in astronomy. He wanted to know all about the stars. And it turned out the teacher was very, very enamored with telescopes, which are wonderful. So he had a course in telescopes. They're making the diagrams and all, but not the stars. So he was learning the tools of astronomy and the coordinate systems. First day. Teacher says, well, if you want to learn astronomy, you got to know about coordinate systems. And went all through coordinate systems, polar coordinates and all that. And my friend came back and said, any interest I had in the stars has just been killed today. I said, really? That's Scout's honor. I said, Walter, hang on, it'll get better. Well, he's weeding out the class. Yeah, he wants the class smaller. Okay. What we're going to do here, gang, is we're going to equate these two. If this is equal to this, why don't I just write it like this? Whoops, okay. I should have wrote it the other way first. Can I cross multiply? How many say no? Stand up. And can I shorten that? I'll put it right up here. Delta t is a time interval. Let's just call it t. Time interval t. And can I put the delta sign over here? The change in velocity is the same as the change of... When you see a discrepancy in the workbook and the text with this, you'll know what it means. Delta t means how many seconds. And fine, we'll keep the delta. Okay. This is what we're going to talk about today. And that's how we get it. It's another version of Newton's second law, isn't it? Nothing new. It's Newton's second law. When you push something, how far it moves depends upon how long you push. And if you push something, how long you push depends upon how fast it's going to go. You pick up speed. In your class, you'll talk about various examples of these. It's just, here's the sheet music. Let's sing some songs. And I'd like to have my kids look at these equations as a musician looks at sheet music. It gives you the connections. It tells you if you make this big, this gets big. You make this small, this gets small. And now they can kind of have a handle for figuring out things. And if you look in our notes, you see I have them divided into increased momentum, decreased momentum, and finally conservation momentum. I found in my teaching it's very important that you don't mix your examples. People get all mixed up. And so what you'll want to do is, in giving examples of this, is you'll want to talk about only the cases that increase momentum. See that golf ball sitting on the floor here? It's at rest. Does it have any momentum? And we've already talked about momentum as being what? A huge truck coming down the hill with no brakes. That's momentum. It's inertia in motion. Moving inertia, momentum. Or a little roller skate has more momentum if it's moving compared to a truck at rest. Things like that. And here's that golf ball sitting at rest and it doesn't have any momentum at all. How can we get that ball to have some momentum? Hit it. So I hit it with a club. And when I hit it with a club, I apply a force. And I make the ball move. If I want the ball to move faster, more change in the velocity of the ball, I won't change the mass of the ball in this case. I'll change only the speed of the ball. And if I wanted to have more change in speed, what should I do? If I want to make this number big, what should I do, gang?
Bigger force?
I make a bigger force, honey. So I hit it harder. Wham! And now I'm finally hitting it as hard as I can. But I want this number to be bigger. And I'm making this as big as I can. Do I have anything else to make big? And that's the time. If I can make the time bigger, if I can hit it in such a way that the time of impact gets longer, let's suppose I hit it as hard as I can, and I hit it in such a way by following through, so I can double the time of impact. Check your neighbor. How much faster will the ball go? Begins with a D. Rhymes with trouble. What is it? Okay. Double. Now this is controversial as to whether the follow-through really does increase the time. And I've seen articles in the Physics Teacher magazine that contest that. But at this point, I think we can say it kind of makes sense that if you do follow through, it hugs the ball for a slightly longer time. And if it's a slightly longer time, that's a slightly longer greater velocity it gets. And if that's what the name of the game is, then follow through. So you're doing both of these.
So what do you mean by follow through?
Oh, by follow through means instead of hitting the ball like that, boom, follow through. And so when it hits the ball, it goes like that, see? Rather than like that, see? So you wouldn't see a golfer go like that. They usually always go like that, see? They're following through. So you want to follow through when you hit. Follow through ostensibly increases the time of impact, and you increase the velocity. And by the way, what we're talking about right now is something that's very important in general. And that is, you can't change only one thing. A lot of people think they can make some change and that's it. It's the end of the story. That's not true. You change one thing, you change another. And if I change in any way either of these two, if I change one of them, something else over here has to change. And every time you put an equation on the board, you illustrate that. And you can't overdo that. A lot of people don't. There's consequences to actions, et cetera, but you can't change only one thing. And any equation will show you that. Now I'm going to talk about making a cannon fire faster. And the other day we had a delightful demonstration with a blower. When you made the barrel longer, what did you do? You got then more time. We could put that in energy, couldn't we, too? Say more distance. Right now we're saying how much speed change you get depends upon how long you push. And how long you push is measured in what? Seconds. Later on we're going to say how long you push can also be measured in meters. And then we're talking about work. That's right. Now we're talking about impulse. Well, I haven't defined this, have I? This is called impulse. This is called momentum. And so impulse equals change in momentum. If you double the impulse, you'll double the change in the momentum. You triple the impulse, you'll triple the change in momentum. You might not triple the momentum. You'll triple the change in the momentum. Very important distinction. I've only used examples so far that make this bigger. In your teaching, be sure to do that. Stick with one. I'm making this bigger. And I've used 3 examples, maybe that's enough. Then I can shift and say, how about decreasing the momentum? Let's suppose I want to decrease rather than increase momentum. Let's suppose you're driving down the hill, driving down the street, and you're in a car, driving, and all of a sudden the brakes go out. And you want to stop the car because there's a whole lot of kids up on the road. Good kids. Well, kids that remind you of yourself when you were a child, okay? Yeah, definition of good kids, right? Not those other ones, okay? Now, you're driving down and you got to stop your car. You got a concrete wall over here, you got a haystack here. Which would you bump into? If you didn't have a knowledge of physics, you'd probably say, well, 50-50 and maybe take the brick wall and get all hurt, right? It turns out you'll be better off if you hit the haystack. Shall I convince you of that? Just joshing here, of course. Here's a trick question. You're going to hit the brick wall and come to a stop. You're going to hit the haystack and come to a stop. Okay, boom. Someone says, hey, hit either one. You're going to get the same impulse either way. Check your neighbor and say, is that true or is that false? How many say same impulse either way? Same impulse. Hands up. Hands up. Look at the people with their hands down. And this is another one of those things like the ball going off. Which ball wins the race and which one's going faster? 2 different things, right? And so here we find out what? The impulses are the same. But students will say, no, if you hit the brick wall, there's more impulse. No, there's not more impulse. You guys are trained. There's more force, more impact force. So again, we're distinguishing between the force of hitting and the impulse of hitting. 2 different ideas. So the impulses would be the same because the momentum change would be the same. But here we can see that if you hit the haystack, it's a small force involved over a long time, and that same quantity if you hit the brick wall is a short time with a large force. In both cases, the change in momentum is the same. In both cases, the impulse is the same, but the forces are different. Here we're talking about critical thinking, distinguishing between closely related ideas. In this case, it's impulse, a new concept, and force, a familiar concept. And usually we tend to answer in terms of the familiar. So our job as teachers is to say, hey, look more carefully. Because someday someone's going to come up and they're going to give a contract to you and say, just go ahead and sign it. Oh, don't mind that the words are a little bit different than you used to. Just go ahead and sign it. You don't want to do that. You want to distinguish between closely related ideas. And that's the lesson here. Then we have circus net. You're standing up on a skyscraper. There's starting to be a fire behind you. You look down, you see a great big circus net. You look down, you see there's a concrete parking lot. And you're going to take a jump, all right? You learned in your class that when you hit either one, the impulse is going to be the same, so why not? Just take the car. No, come on. It's obvious. If you hit the circus net, what's going to happen? You're going to elongate the time during which your momentum changes. By elongating the time, you're going to decrease the force. So there's another one. So why is it when you're roller skating in the roller skating rink and you fall down on the floor, you're okay? You go out in the street in Victoria Park and you skate and you fall down on the concrete, you get hurt. Someone says the floor got more give. Yeah. Which might say, why is it that when you fall on the floor with more give, you're less apt to be hurt? Or you have some glasses, some china falls off onto a carpet, it's okay, you pick it up and put it back. Fall onto a hard floor, it smashes. Someone says, oh, the carpet's got more give. What's meant by saying the carpet's got more give? And then you're reinforcing the idea again. Not that it's got more give, it's that the more give means it will take a longer time to stop. A longer time to stop means a shorter force of stopping. So that idea is the next one, huh? Familiar examples. Boxing, why is it that a fighter, why is it that we have the one of the boxers there? Why is it that in boxing we ride with a punch? Well, what happens when we don't ride with a punch? I used to think I knew the answer to that. I used to box when I was a kid in high school. And I used to think that when you pull back, the velocity of the punch will be less. And if you come in like this, the velocity of the punch will be more. And I had it down. And I felt good that I could kind of figure things out. And I didn't know anything about physics or anything like that. But I knew coming back, it doesn't hurt. Coming in, you're in trouble. And I knew why. It's kind of nice to figure out why things happen, see? So it's a different speed, see? Less speed, more speed. I had it down. One day I'm looking at my old Ring magazine. It talked about Joe Louis. You guys don't know who Joe Louis is. Joe Louis was a fighter, 12-year champ, heavyweight champ, honey, back in World War II. You guys know about World War II? Read your history books. All right. And he was called the Brown Bomber. And that Brown Bomber, they timed his swing. This is before photo gates. There was a time before photo gates. You know that? And that guy could throw a right hand, throw a right cross. Boom. They timed him at 90 miles an hour. 90 miles an hour. Ooh. That means if he throws it at 90 miles an hour and I pull back, I'll be okay. But if I come in, I won't be. You guys look. How many miles? Oh, can you do miles per hour? Yes. It's part of my rap. How many miles per hour do I go back?
Not 90.
No, not less than 90. Excellent. We take an estimate. How much? 2 miles an hour, huh? 2. Okay, so 90 take away 2 is what? 88. Now how about like this? 92. Gang, 92 miles an hour and 88 miles an hour. Same. There's not that much difference. So it can't have to do with relative speeds at all. And that's what I thought. And I figured out, and I was bothered. And I could, well, gee, there must be some reason. And of course, I found out the reason. You know, what happened to George Foreman? George Foreman was just a nobody. And one day he went into a library, picked up a physics book, and he saw this equation, and that son of a gun became heavyweight champion of the world. Okay? Because this tells why it is, you see? Let's suppose that punch is coming in at you, okay? Boom. Now, what's MV and what's F and T? We want the kids to figure these things out. What would MV be? What would M be? Someone punches you. Boom. No, not your head. No, let's talk about your head's going to be. Well, you could say your head hitting the fist, and the poor guy. Oh my God! Look at what he did with his head. Okay. But let's think about the punches coming in as a force on you. Well, that force is due to the change in momentum of something. In a barroom brawl, it would be the mass of the guy's arm, probably. What'd you say about my butt? Okay, fight like that. Oh, like that. You don't see fighters going like that. You see fighters going like that. Whoa, 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 straight. See, the body's in it. For a barroom brawl, M's the mass of the arm, probably. Get George Foreman or someone like that. Boom, probably from the knees up. Boom. Whoom, the whole body. Now, a lot of your body. M is big. V is that whoom thing coming in at you. Oh, here it comes. Now you're going to stop it. You're going to change that momentum right down to 0. And when you do that, unfortunately, you're going to have to provide a impulse. Somebody says, get it over quick. Good idea or bad idea? Very bad idea. So what you want to do is you want to ride with the punch. Why? Boom. You want to make that punch last as long as possible. By extending T, you decrease F. And there it is. Boom. Not relative velocities, but relative times. And so many times in questions we get mixed up, velocity, time, and here's one of those. So you just increase the time. Now, it's something that I couldn't figure out when I was a young guy. I used to do a lot of boxing, and you'd go in the gym, and you hit that bag all afternoon. Bam. And you don't get tired. You feel good, man. At the end of the day, you got a good workout. You feel good. Now, you go, tournament comes Friday night, and you're in the ring for 3-minute rounds. Only 3 of them, amateurs. 3 rounds. That's 9 minutes. Come on, 9 minutes. I can hold my breath for 9 minutes. I'm exaggerating. Tell you what, at the end of that first round, you come back and you're tired. At the end of 3 rounds, you are pooped. And I never could figure that out. And I had my idea about that. I used to like to analyze things. And my analysis was that it was psychological. Is that when you're in the gym, there's no one watching, you're just doing your thing. You know, you're expending energy. But that night of the tournament, all these people looking, your father's out there, you can hear them calling you and things like that. And you just get sort of psyched out. So I said, I got to go in there and psych myself up so I'm pretending I'm in the gym. I can fight all day long. And it turns out the answer has to do with what? Do you ever see someone go 15 rounds? How often do they miss? Amateur fighters, how often do they miss? What happens when you miss? So here's the guy here. Here you are in the gym. Boom! Boom! What stopped the punch? What provided the impulse to stop that momentum? What provided the impulse? The big bag, right? The bag, honey. The bag. The bag did it. So you hit the bag again. Boom! What stops the impulse? The bag. Now, tournament night. Boom! Whoop! He's not there. He's down here. Does your punch keep going forever? No. The momentum of that punch is spent. Who spends it? Who provides the impulse? You do. You do. So you punch yourself out. And so a good fighter will make the other guy keep missing, because they're talking about not momentum, they're talking about the next chapter. What is it? Begins with E. Energy. Conservation of energy. You know those Rocky films? Baloney. It's not like that. Where the guy, when all of a sudden he comes to life. It doesn't work like that. No, yeah. You've only got so much energy. See? In fact, even I see these guys, these are all doing all the shadow box before. I'd just sit down. Yeah, I'm gonna, I ate my bran and all that stuff that you're supposed to eat, and your eggs and your tea and all that. But I know I had so much energy. I want to spend it up there in the ring, not beforehand. There's something to that. There's only so much energy. You eat your food. Where's that all come from? Yeah. And so you de-energize yourself by throwing punches that miss. And again, you can relate that to here. And then karate. Watch this. I'm up to my white belt, by the way. See this great big log? See, 4x4, oak, no, hemlock, like the baseball bats, all right? Watch this, I don't want to hurt my hand. Now I'm going to break that right before your eyes. You guys in the back row, you can stand up, it's okay. Okay, here we go. How about like this? No. I got to go like this. Boom, look, splinters. You see that? Did you see that devastating blow? Quick time or short time?
Short time.
Short time. Short time mean what kind of force? That's why I almost hurt my hand. And no matter how much force it takes to break that board, how much force will act on your hand if you have a good hand? A practiced hand. How many say exactly the same amount of force but in the opposite direction? Exactly as much? Exactly? People that say exactly as much force, stand up. Stand up. I want to see who you are. Stand up. Stand up. Stand up. Stand up. Stand up. Stand up and be counted. I believe in Newton's third law. Look at these people sitting down. Is this comfort? No. You hit the board, yay. Yeah, it's exactly the same. And you got to tell your students will ask you about that. Yeah. That's what all the training's for. And your hand is kind of resilient, isn't it? Okay? It does crumple a little bit, right? You got to hit that right. Because the force that you take, the force required to break that board is the force that is exerted back on your hand. The force that you exert on the board, honey, mortgage your house and bet on it, is the force that the board exerts on your hand. Don't lose sight of the fact. Newton's third law holds. Because the kids can talk you out of it. And then if you're not sure of yourself, they can get you saying, well, I guess it really doesn't hold for the case of karate. Oh man, now you're on the frying pan. So stick with the law. There may be other complications, but one thing I know, and then you got that. And now you're teaching physics. And you're not expected to know everything about everything. No way. We're not walking encyclopedias. And it's okay to say to people, hey, I don't know. I'll tell you a little story. A young lady I know some years ago was asked to teach the conceptual physics course when it first came out. She was a biology teacher. And she says, God, I can't teach physics. I don't know any physics. And the principal says, well, you're on. And so she told the students, hey, this is my first time teaching the course. I don't know jack about this stuff, and you don't either, but I tell you what, I'll do the best I can. And if you have questions, ask the questions, and don't be disappointed if I can't answer them. And she found that her success in that class was considerable. And she has a new technique now. In biology class, where she is very, very comfortable, when students ask her a question, her answer will be, well, what would we have to know to answer that? Let's think about that. Rather than spit out the answer right away. And so, if Burl Gray had spit out the answers to me right away of all the questions that were posed, I would probably be painting signs today. Lived in Colorado for some while. And in Colorado, lived in mining country. It is long, long trains of ore, like 80 trains. But the switching yard's right there, and I'm in earshot of the switching yard, and you're trying to sleep at night, and the train starts up, clunk, 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 80. Now they're all going. Now he wants to stop. Clunk, 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 80. Now he wants to switch tracks. I'm thinking to myself, why don't they take those couplings that are all clunking, tighten them up so they don't clang against each other. And boom, all of a sudden the physics came through. Ooh, I got a new example for impulse and momentum. And what's the answer, gang? Do you think you can get 80 freight cars loaded with ore, moving with a couple of wheels all together at one time with these steel wheels hitting steel track? NWH. No way, honey. It's not going to happen, okay? Those wheels are just going to squeal and they're going to make sparks, and there you go. It's not going to happen. But the locomotive can pull one car. It can get one car up to speed. There's enough friction there. And so it does get one car up to speed. Now that car is moving. You see the rest of the story. Then it can pull another, and then another, and then another. In effect, what's happening is delta T is being extended for the same friction force. And you can get moving then your whole load. So you pull one at a time, one at a time, one at a time till you get right up to speed. And I liken that to students taking courses. You don't take all your courses in one semester. You spread them out. And then another thing that's nice. If you have a system whereby the force is 0, then no change in momentum is possible. And we believe so strongly in this law that we can say that. Give me a system where the net force is 0, then the change in the momentum is 0. And that brings you right into a whole great big foundation block for physics called the conservation of linear momentum. And that is, in any system, without a net force acting on that system, whatever momentum that system has, that's the momentum you're going to keep. And you'll keep it forever You'll keep it indefinitely until some force acts. So now we say delta mv is 0. We call that the conservation of momentum. Whatever momentum you happen to have, it's not that the momentum is 0, gang. Make that distinction. The momentum is not 0. The change in momentum is 0. So whatever momentum you have persists. And that's one of the cornerstones of mechanics, the conservation of linear momentum. See these air tracks I have here today? I don't have them. But you guys have them, and then you can play your little games. But that's the thing. Before you start playing those games, or before you finish playing those games, liken that to here. This is the relationship. And that comes from Newton's second law. And everything you're talking about with momentum is in terms of that relationship. And you always come back to that relationship. There's the music. And with that musical score, you can play all kinds of tunes. Examples, 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 examples of many of them. And always relate them to that equation. That's the way I teach. I teach equations. These equations show what's connected to what. This gets bigger, this gets smaller, all that sort of thing. And then the grand finale is when there's no force at all. And there's no force at all if you define your system properly. Ooh, somewhere here I've got some practice things that you guys have never seen. Brand new. You know what I'm supposed to be doing now pedagogically, you guys? Do you see I'm flubbing around here? If I'm going to flub around here, what should I do before I start to flub around? Give you something to do, or ask you a question and ask you to check your neighbor. The check your neighbor routine in my teaching is the best thing I can say to do. My classrooms are the noisiest on campus. You come into the class and everyone's talking. And my role, I used to get up there and give lectures. But I still do that to some extent. But a lot of it is throwing things out like a conductor. You know, you're conducting and asking the kids to check and talk about things. And while they're talking about things, then you can look at your notes and see where you are. Gives you a little time to catch on. Or you can start to do stuff like this. Hey, I know what I want to talk about, talking about eggs. Do you guys know why an egg is shaped the way it is? Did you know if you put an egg between your hands like that, you can't break it? Why can't you break it? You can't do it. And an egg is more rounder on one side than the other, right? So how does it roll when it rolls out of the nest?
It doesn't.
Into a circle. And that's nice, isn't it? But an eggs, they get that particular shape. Why that particular shape? Well, do you guys know why the St. Louis Arch is shaped as it is? Do you know what the shape of the St. Louis Arch is and down on the mainland? It's called a catenary. And the shape of that arch is the same as the shape of a chain that would dangle. When you hold a chain up by two ends, the chain dangles. And what's the tension between links? What's the direction of the tension? Assuming that the mass of each link is small in comparison. Isn't that right along the chain? Exactly along the chain, right? In fact, that's why it hangs the way it does, doesn't it? Now, you know when you take blocks and you put them up like this, the ancients used to use circles. Go to Europe and look at all the ancient ruins. They're all circular. They had to think about the divineness of circles or something. But the trouble with that is I put a load on them to splay out over here, so you got to make sure you got a big brick wall. But go to see the St. Louis Arch, and you don't see anything holding it in like this. It's just going up like that. It's the shape of a catenary. And every one of those blocks is pushing against the other block, and the compression forces are guess in what direction? Splaying out a little bit? No. That's a circle or some other shape. But a catenary right along. So the weight pulling down, it's not going to spew out. Just that shape. And as I understand it, that was not known until Robert Hooke, a contemporary of Newton's, discovered that. And he told his friend Christopher Wren, who was wanting to design the dome of St. Paul's Cathedral in London after the fire. And he wanted to get a shape that wouldn't splay out. Look at this Notre Dame Cathedral, where they got all this buttressing and everything, because it's going to collapse of its own weight and push out, yeah? And so when Wren learned that, he made the cathedral the shape of a catenary. It doesn't splay out. And today, when you look at domes, guess what the shape is? That of a chain hanging underneath. And so what I did recently, I took a little chain, and I put an egg next to it, and guess what? It's a catenary. You've got a steep side, then you turn the egg over, then you hold it, pull it up a little further, and you get another catenary. So an egg is a double catenary. So when you squeeze it, you might as well be squeezing a solid. There's good physics. Well, honey, that doesn't have the same momentum it had when it was falling. So would you say that momentum's conserved? Oh, well, sometimes it is and sometimes it isn't. Depends on what example we use. Hey. You know, that's not doing it. So what do you mean momentum's conserved? And where the little catch-a-rooney is system. Who's got the system? Like that game as a kid, button. Who's got the button? So what is the system you're talking about? And so I have a practice sheet here that is not part of the high school program. This practice sheet is in the college book. Here we have a couple of blocks here with a spring in between. Boom. When the spring is released, the force on each block will be the same. Of course, the accelerations will be different. Now we get some questions. Does an external force act on system A? Well, yes or no, gang? Check your neighbor. Here's one system A. Here's one system B. Is there a force acting on A? All right. Is that force acting over some time? Then A ought to go a change in momentum. And we can't say momentum's conserved there because all of a sudden we get more than we started with. So momentum is not conserved for system A. Get it? There's a change. There's a force acting on the system. Boom. Momentum changes. How about momentum B? Yep. There's a force acting on momentum B. And here what I do is I can isolate that force with a dotted line. See that? System A, there's a force poking from the outside into my dotted line. So, whoom, away it goes. Same with B. So when I said, is momentum conserved? If you said yes, you were thinking of the system, the world, and the pen. If you said no, you were thinking of the system, the pen. So you got some people here saying yes and some people saying no, and you're both right. But it depends. You've got to link that to the system in question. If I take as my system both blocks, and believe me, when you're teaching this stuff, and if you're new at it, you can really get in trouble with your kids. Get all confused. And that confusion is the failure to distinguish between the systems and whether or not is the net force acting on a system or not. Now take a system of both together. There's no force. The forces are internal to the system. That's like you're in a car, and the cars get a dead battery. And it's a clutch type car. Give it a little push, boom, you can catch it and you're all set. But you've got your new threads on and it's a rainy day and it's muddy outside. And your friend says, get outside and push the car. And you say, well, why don't I just stay in here where it's comfortable and sit in the seat and push on the dashboard? Now you push on the dashboard, but what happens? Are you exerting a force on the dashboard? Yes, dashboard's exerting a force on you. So it cancel out, yeah? All right, get outside the car. You push on the car. Does the car push back on you? Well, they cancel out too. You might as well stay in the car. Check your neighbor. What's wrong?
What's wrong?
Oh, what's right? Why is it that you can sit in the car where it's nice and, sit in the car and push? You're going to get the same physics inside the car as outside the car. Why is it you have to get outside the car? When you get outside the car, you push against the ground pushes against you, and if you want to say you still are part of the system, you and the car now have an outside force. That ground is pushing you every bit as hard as you push on it. And that's an outside force acting in the system. Boom, the system moves. All right, over here we got a little practice. If you had this at your sheet, A hits B. Draw only the external forces that act on each system. How would you draw the force on A? Wouldn't you draw a dotted line like this? And then for B, wouldn't you draw a dotted line here? And then for C, wouldn't you draw a dotted line here? And if you want to draw the vectors, you'd have a vector over here. No, in system B, you'd have a vector coming in like this. Let's look at this. System A is hit with a force like that. So system A changes its momentum. System B is hit with equal and opposite force like that. So B changes its momentum. Both, they cancel out because these forces are both acting on the same system. So they act out. And the system is AB. So there's no net force here at all. So this momentum doesn't change. This does, and this does. This ball slows down and stops. This ball speeds up and goes. This ball just transfers whatever momentum it has to the other part of the system. So the net change is 0. So there's your 3 systems. Very important to do when you're talking about conservation of momentum. If you talk about conservation of momentum and you don't identify your systems, then your students will spit back the examples you give, and if you give something off the curve, they're dead. You've got to teach this part here. Here we have the little girl. She jumps up and down. Okay. Little girl jumps upward. In the sketch to the left, draw a closed dashed line to indicate the system of the girl. Wouldn't that be like that? Okay. Is there a net external force acting on her? Yes or no? We don't understand that force very well, but we have a name for it. What do we call it? Gravity. That's right. And there it is. So the momentum of the girl changes. Now, does her momentum change? Yes. Is the girl's momentum conserved? Answer begins with an N. No. Good. Okay. So no change. Now, to the sketch to the right, draw a closed dashed line to indicate the system girl and Earth. We have a force like that and a force like that. They are internal to the system. There's no net force on the system, so the system experiences no change in momentum. And you can kind of show that. You know what happens when you stamp on the ground. Watch the whole floor, or I jump up in the air. Listen to, see if you can't feel the earth dip down like that. You get it? Okay, good. All right. You're good. Now, if I were big, then you could keep going up, and but you're into that. Always exaggerate your circumstance when your principles aren't evident. You know, if you want to make something move, you push. And how much you make it move depends upon how long you push. And we talked about that. But so far we said how long was what? Time. Now we're going to say how long is distance. And here's one of the cornerstones of physics too. We call this quantity here work. We call this quantity here energy. Energy is nature's way of keeping score. It's a difficult concept to grasp. The only time we can grasp energy is when it changes. If there's no change, we're unconscious of it. For example, we all have energy in this room, many kinds of energy. There's no notice of it unless something changes. So the key thing with energy is the work that you produce. And when we talk about work, we're talking about a force that's exerted on something and moves that something a particular distance. I can come over here and I can push this wall. And I'm going to push it for about 3 hours. Is any work being done?
On the wall? No.
Very good, Peter. Very good. On the wall, no. How about on me? Yeah. Come up and look with a microscope and look at the muscles quivering, moving, forces and distances. I'm going to get tired. In fact, I could lose weight pushing on this thing enough. So I'm doing work. There's work being done on my muscles, which are moving, but there's no work being done on the wall. So really, when you're talking about, again, system, who's got the system? Or what system are we talking about? Work done, as Peter said, on the wall, no. So get that. All these examples of is work being done. On what? By what? That's a distinction to make. If you take an object and lift it up, if I take this object and I lift it, I'm doing work and elevating it. I'm doing work because I'm having to exert a force and I'm lifting it up a distance. If I double the distance, what will happen to the work done? Double. If I double the force that's required to lift it, what happens to the work? So you can answer all your questions in terms of the sheet music. Here's the sheet music right here. Here's the energy sheet music. Here's the momentum sheet music. And so you can answer all your questions in terms of formulas. Again, I know a lot of teachers that say, I don't want my kids groping for a formula when I ask them a physics question. My particular style is exactly the opposite. Because when someone asks me a question, I grope for a formula. That's what I do. And I like my students doing that too. But the formula is what? It's telling me what the connections are. So it's a simple question. double the distance without changing the force, honey, you get double the work. And double the force without changing the distance, or double both, and you get 4. I think this is a nice way to think. It tells you what the connections are. In fact, it's so powerful that if you ask a professional physicist any mechanics type problem, they will probably first think about this. They won't think about the kinematics equations. They'll think about this, if there's something moving. And if things are colliding, they'll think about this. In fact, I think if I was writing my book all over again, I'd almost start here. If people are going to spend a whole lot of time, they ought to stand right here. This is heavy, heavy stuff. And the kinematics, I think, is lightweight because what are you doing? You develop the concepts of speed, velocity, and acceleration. What's the big deal? Don't take too much time doing that. That's my advice. I'd rather spend more time looking at something like this. Which is to say, whether or not you do work on something will depend upon whether there's a change in energy. And when I pushed that wall over there, that wall, the energy of that wall stayed the same. So no work was done on the wall. But while I was pushing, if you put a thermometer on my skin, you'd see it go up. So I changed energy there. And over here, I put an E. Oftentimes people put a KE. No, I like E. And I don't even distinguish between conservative and non-conservative forces. I just say, honey, you do work on something, you'll change the energy. You say, but the energy doesn't change. Then no net work was done. Throw a ball up in the air. Work being done? Yeah, slowing it down. We're speeding it up. It's right where it started. So coming up, coming down, they canceled out. One's going against gravity, one's coming with gravity. But I don't get into tricky things like that either. I'd rather do things like this. First of all, kinetic energy, different kinds of energy, gang. It turns out force times distance. Let distance be 1/2 AT squared. Let force be ma, and you pretty soon come to. And you're all familiar with that derivation. And I'll call that energy of motion. Or if I just want to lift something up, then the lift up will be the weight, if I lift it without accelerating, the weight mg times the distance, call it a height, vertical height, and I'll call that energy a potential energy. And there's all different kinds of energy, and what we'll talk about is just mechanical energy of these two forms, because that's a lot. And later on we'll find out that these relate to heat, sound, electricity, so it keeps spreading. But at the beginning, just these two forms of energy, the interplay between those, and the work required to change both of those. Lifting a piano. Someone wants to lift a piano. They got the pulley system. The force you pull down times the distance you pull is the work you do. And that work you do will give you the mgh, the amount of height it will go up. And so that's kind of nice. Jacks. You get a jack, push down. Force you push down times the distance you push down is the work input. The work output is the weight times the height it comes up. When I was a kid, across the street were some older boys that were into automobiles, and I remember a conversation they had. It really, really intrigued me. And the conversation was, when they were fixing their automobile, was that there was conspiracy in Washington, and the patent office was holding behind these designs that would allow cars on a liter of gasoline to drive from New York City to San Francisco. And the reason that you had to spend more for gasoline was because they were holding behind this device, which you'd put on your carburetor, and it had magnets, of course. And these kids were older than I was, and they were sincere, so I, of course, believed it. And it made me start to look at the whole system a little differently. They're holding it back from us, and the oil companies are treating us unfairly and all that. Well, there's a little thing I didn't know. I didn't know about this. Let's look at that. What I didn't know is that in the gasoline in the car, you have a certain amount of energy. And if you burn that gasoline and to get that energy out, that energy will push the car with a certain force through a certain distance, and the product of the force and the distance in no way can be greater than the change of energy, converting from potential energy of the fuel to the energy that gets the car across the field. That's the energy you have to spend. And this is a concept that people don't know. The general public doesn't know this. If that's the energy that's in that car that you're going to convert to mechanical energy, then what's the force that you have to, that's required to push a car? Find out the force required to push the car. You can put a bathroom scale at the end of the car and start pushing. You can measure it. Take that force, multiply by some distance, and the most that product can be is this. So it turns out the force is usually about 500 newtons at highway speed. 500 newtons. It takes 500 newtons of force to keep the car going in level ground, mainly due to air drag. And that 500 newtons times some distance d is going to equal this. So that distance d (5 and a 40), 8, with a 1, 2, 3, 4. That's going to be 80 kilometers. So the upper limit for that particular car, that particular gasoline, is 80 kilometers in that 1 liter of gas. And those guys that were telling you about the magnets in the carburetor were full of it. They didn't know what they were talking about. This is nature's limit. The world behaves this way. That's the way it is. So if you're hired by Detroit or some car manufacturer to increase the gas mileage in cars, what do you have to think about, gang? Make this more, get more energy in your gasoline, or
Make that less.
decrease the force that's required to push the car. And you know what you put after that? Period. And that's what it's all about. And when you see all those people hunched over their chairs doing all the plans, that's what they're doing. They're trying to make this less, because you want this to be as much as you can get. So what do? You streamline your car. And I haven't even talked about efficiencies. Then you get about a quarter of this efficiency anyway. So it'll be cut down to a quarter of 80, whatever that is. Okay? But this is the way you think. We want to get our kids thinking in terms of things like this, rather than grand conspiracies and all this stuff. At least get this part down so you know what you're talking about. I want to show you a little bit thing on problem solving. In my conceptual course for non-majors, I don't do what I'm doing now. A car traveling along a level road at speed v slams on the brakes and slides to a stop. Coefficient of sliding friction is mu. How far does the car slide? Give me the solution, please. You have 30 more seconds. I got to tell you a little story. When I was in college, my second year, I was taking electricity and magnetism, and that course was a bear. It was tough. And the instructor gave us a lot of problems, and we'd have to solve those problems. And we worked hard at solving those problems. And it was really sort of annoying to come in the next day and to see Professor Block effortlessly whip through the problems. How did he do that? This guy got to be some super genius. I mean, he'd just get up there and boop, 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 right on through and then circle the answer and say, any questions? Well, when I was in school, I really was a shy guy. But I remember one day I said to him, Professor Block, I have a question. He said, yes. I said, you know, when you do these problems, you make it look so easy. But it seems that once you get started, the rest, you could almost just stop because we got it. My question is this: how did you know to start with how you started over here? How did you know to do that? Because that's where we're having our problems, is getting started. And the answer I got, I didn't like. And the answer was, well, it turns out if you work out enough of these problems and work really hard, and that's what I didn't want to hear, man. We were at capacity already, as if that was the only course we were taking, okay? If you work really hard, you'll start to build up a savvy. And before you know, you'll start to be able to get the knack, and it will come. Stay in there. I didn't like it. I want to share with you what my answer to that question has evolved to be. And my answer to that question is, hey, what's the grand principle that you're looking for? Or we could also say, draw a sketch. What's happening here? A car is moving, slams on the brakes, and comes to a stop. What is the most general way that we could look at that problem? From what general principle?
Energy.
It'd be energy, wouldn't it? The work-energy theorem. Isn't that right? That's the general principle. I mean, that would count for kinematics problems too. Work-energy theorem, which just says the work you do will change the energy of the system. So here's how I instruct my students to solve a problem. State what the general principle is, and say from that, which in this case would be some force times some distance equals the change in what kind of energy in this case, since it's a level ground? Kinetic energy. From that, write down an expression for what you're looking. And if you do that, I'll give you 40% credit. And if you use the proper equation, I'll give you 50% credit if you go no further. So how about a student does this? 40% credit?
That's not what you're looking for, is it?
No, that's not what I'm looking for. I'm not going to give him any credit at all. How about this? 40% credit? No? How about this? That doesn't do it? How about this? That's what I'm looking for. The question says, how far will the car slide? How far is distance? So I say, just put D equals, I'll give you 40% credit. And if they just go ahead and go through all the problems and just do that, I think it's worth 40%. Now, if you want a little bit more than 40, D equals what? From this, D equals what? D equals what's the force? Let's look and see what we have over here. Looks like we have a force of friction like this. Any other forces acting? Well, it's moving this way. Is Clark Kent here today? No, okay. The rest is duck soup gang, huh? Because what do we got? The change in kinetic energy coming down to zero is simply going to be 1/2 mv squared. Well, that's the v we started with. Call it v sub naught. There it is. And the force is going to be the force of friction. And the force of friction is what? Mu F sub n. F sub n is going to be what?
mg.
Because it's level. I give now full credit for that. The bit is this. If you start with the general principle, from that, isolate the thing you're looking for. In this particular case, it's distance. I could have asked, what's the speed if I gave him the distance? Or I gave them both, I could say, what's the coefficient of friction? Then I could solve for that. What else could I solve for? You get the idea. But once it's almost mechanical. So from this, we get that. Now let's start and go right here, and you could just come right down. The delta, that's the whole change. Boom, this is that. Bottom, force of friction, mu, F sub n. Then we go over here, this stays the same. Now what's this? Put this in here, boom, done. In fact, you know how you have this thing where you're trying to get your students to save, to not put their numbers in until the last step, and they won't do that, and they start plugging numbers in right away, and you're wondering, how can I get them to wait until the last step and then put the numbers in, and everything you do won't succeed, and you don't know what to do about it? That's like in Philadelphia when they had the streetcars. People used to stand on the running boards, and they'd stand on the running boards and have all kinds of accidents. And finally they come up to an engineer and he says, what can we do about this problem? People are standing on the running boards and having all kinds of accidents, lawsuits, and da-da-da. The engineer says, well, let's make it so there's no running boards. So as soon as the car starts to go in motion, the running boards fold up. So get rid of the running boards, okay? So what's the thing here? Get rid of the numbers. There's no numbers there, gang. V, mu, that's it. There are no numbers. And if you came to City College of San Francisco and took my exams, you'd find they have no numbers. So I've solved the problem. I don't have to beg and preach to my kids. That's the answer right there. Furthermore, the answer makes sense, because the distance I slide is going to depend upon how fast I'm going. The greater the speed, the more the distance. And the greater the coefficient of friction, the shorter the distance. The more G pulling down, the shorter the distance. It kind of makes sense. And there it is right there. No numbers at all. No number crunching. Alphabet crunching. But I'll tell you, when I look at other textbooks and I see how the problems are, they'll usually set it up and they'll begin maybe over in here somewhere. Or they'll begin, they won't begin right here. And after they've got all that done, then finally they put D equals. So my thing is go right for what you're looking for. If you're asked for distance, I want to see it here. I don't want to see all this mumbo jumbo and finally you got the distance right. Now, this is my technique. Do it here. Boom, it's clear. Under pressure, you're on. You don't look for the mass because it's canceled. You keep going. Let every term here dictate the next step. So the step is dictated. Isn't that how a computer works? There's a little story here, and it's an interesting story. And I just realized it as I was talking. This is what I do with the students who aren't conceptual. And this technique is something I have a passion for. And I'm giving a conceptual physics workshop. And I'm sorry, I'm a human being. I can't resist sharing my passion with you. In fact, this is going to be on the exam Friday. You will find there will be times in your class you'll read some article that's way above where your students are, but by golly, it's delicious. So how do you resist the temptation of coming in and sharing that with the kids who are saying, oh no? Okay. I don't know, you got to watch that, you got to balance that. Because in our classes, isn't it true? They close the door and you got the kids and it's up to you. So I'm guilty of that. I just couldn't resist sharing my passion for problem solving with you guys in the conceptual workshop. Guilty. This is out of place. This is for those students who go further than the conceptual and get into the application stage. In all of this conceptual stuff, I didn't show you one of the overheads, but it's really activities first, concept development, application. And this would be an application. All problem solving are applications. When I went to school, I never took any course that gave any credence at all to activities. Very little to concept development. And from day one, it was roll up the sleeves and let's solve those problems. Applications right away. And I got good at it. And I got my degree. And I said to my friends, I hope no one asks me any physics questions. And I hope if it is a question, it's a problem. And when I got to graduate school, having no training whatsoever, no instruction in the concepts of physics, we had the dreaded graduate oral exam. And that's the conceptual exam. And where in your training do you get concepts taught? They're not taught because we don't have time. We've put the cart before the horse. Problem sets, that's the key. And every course I took was a course in problem solving. And at the time, I didn't see the difference. And when I wrote my book, and my book came out, some people were saying, I didn't think this could be done. Because they were thinking that physics was, by definition, very clever problems. And that's what it is. But I call that applied mathematics. Only after I went through it myself. Sometimes you don't see the distinctions until later on. So I think most of what we're teaching in physics courses are applied mathematics. And it's wonderful, and it ought to be taught. And it's very, very important. But I wish they wouldn't call it physics. Hey, I want to show you something that's exciting. Would you want to see something that's exciting? Get into the next part. Do you guys know why a railroad train will stay on the tracks? Do you ever wonder about that? You're in a train. You're going 100 kilometers per hour along the track. And you go right around a corner. And going around all these corners. And these wheels stay on the track. wait a minute. When you were little kids, you knew that. So you get on quite safely. They very, very seldom crash. You get on, you ride your train. And you don't even think about it. Maybe. Well, let me ask you a question. What keeps the wheels on the track? Why don't they roll off? And then you might think it's that flange. The wheels are flanged, aren't they? But then next time you're at the train yard, I want you to do something. I want you to look at the flange. They're all rusty. They almost never touch the track. So the wheels are somehow designed so they'll always stay on the track. And furthermore, when a train goes around a corner, it turns out there was a problem that the train going around the track, you see, the outside track would be longer than the inside track. And isn't it true that the wheels are connected? It's just one axle and it's welded on there. And when the wheels turn, they're both turning at it's not like a car differential, one can stop and the other one turn. It's just, there it is, huh? And so they both have the same omega, okay, rotational rate. Now, how do you get that with the same rotational rate to go around a corner without making a whole lot of sparks? One wheel going to squeal and scrape. Because one wheel, you got to design it so one wheel will go faster than the other wheel. So you go around this wheel's got to go faster. Then when you go this way, now this wheel's got to go faster. And you know the wheels are designed that way so they can have different speeds. Did you guys know that? And they're all welded together? And I can kind of show you that. Take this. Hey, wait a minute. How come it doesn't roll? How come it rolls in a look at that, gang. It's rolling in a circular path. Why? Isn't it because this part rolls faster than this part? Is that right? If I have a turntable here, which part of the turntable is moving faster? The outside or the inside? Let me put a coin on here. But you guys can see this. Yeah. See the outside one's moving faster? My father used to work on a merry-go-round. And he used to tell me that he'd have trouble with people trying to convince them when they put a little child that's kind of frightened on the outside, that it would be better to put the frightened child on the inside where it's going slower. And they'd say, what? So yeah, the merry-go-round part here is going slower than out here. Don't you see that? In fact, if it's twice as far away, it'll have twice the speed. And what's the confusion? Omega and V. See? Omega and V. So it turns out they have the same rotational rate, but different linear speeds. It's like this ruler is moving now, right? Which is moving faster? This part here or this part out here? Yeah, this part here, see? In fact, if I take the ruler and drop it, the tip of that ruler went down at greater than G. The center of gravity was G when it got level, right? So the wind is whipped. That's why you can take a fly, you can hit a fly. Do you ever try hitting a fly with your bare hand? I mean, if you go right where the fly is, you're going to miss. But get a fly swatter, and what happens? Whip, boom, you get them every time. You're just making the V bigger. And what we have here, the concept is V equals R omega, rotational motion. So the rotational motion rate, radians per second, or revolutions per minute, whatever, is directly proportional to, the velocity is directly proportional to that rate and the distance r. And so we have a cup that's like this. We have a big R here, and over here, a little r. So the way that train stays on the track is rather intriguing. Here it is in the textbook. And we have, what I'm going to do is I'm going to make a couple of wheels like this, and I'm going to tape them together. And I'm going to simulate railroad wheels. And I'm going to take a couple of sticks, a couple of meter sticks. Just go like this. This will stay on the track. And if I had the track curved, and that'd be a nice little demo to make. If I had the track curved, guess what the wheels would do? Turns out your railroad train has beveled wheels, gang. Ain't this fascinating? And you can kind of see already what's going on, huh? It's very much like this sort of thing here. Now here I'm continuing all the way in. I have a very, very wide wheel. They're as wide as they need to be. And those will ride on a track like that. Now when they ride like that, they're both riding on the same radius. The radius is the same for both because they're both riding in here. If r is the same for any given omega, v will be the same. And so when you're riding along the straightaway, you want to ride such that both wheels are, say, right at the midpoint. And here you are, riding along. Now all of a sudden you hit a track, you hit a curve. And all of a sudden what happens? Whoom, by inertia, it gets like that. See what's happening, gang? Which wheel is traveling faster, this one or this one? This one. This one or this one? This one. Do you like it when you're driving down the street and someone says, go that way, and they're in the back seat? Which way? That way. Okay. But isn't that nice, gang? Look at that, see? So this wheel's moving faster, and so whoosh, right around. And then all of a sudden the track comes over and it goes like this. Whoops, so what happens? You overshoot and you come like this, and then and you come right back. And then you come back on the straightaway, and you go shoom, 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 shoom. And you've all been on a train that all of a sudden sometime you feel it swaying. Boom, boom. The train's going this way, and this train is going. What's it doing? Boom, like that. The flange can be used at the rail switching yards when you want to switch through the slots. The flange can be used in an emergency when there's a big wind or something and you're pushed right off. But if you look at the flanges, they're mostly rusty. And here's a diagram of a real flange. See the angle in here, gang? Ain't that nice? Now you can ask your students, how will the angle compare to how sharp a turn you can make? Any correlation? What if you're going to make a very, very sharp turn? Steeper angle? Let's suppose you're going to make no turn at all. Almost no angle, but then you can kind of drift off, so you do want to have some angle in there. And of course this goes all the way down. This is a cross section. The wheel, of course, comes all the way down like this, see? And so it turns out here you have a bigger radius than here. How much bigger this radius is than this one here ought to be how much longer one side of the track is than the other. So be proportional. Along with the book comes a teacher's manual. And if any of you ever teach my course, please, or if you're not, please look at my teacher's manual. In a teacher's manual, you'll find it rich. My whole life is in there. And in the teacher's manual, we have a page that talks about all that. Here, do this demonstration here, do this demonstration here, and da-da-da, and all the things you can do. And it turns out in our textbook, we don't have these wheels. And I couldn't get my editor to put the wheels in. They didn't have room. And so they're not in there. And so for teachers, what I suggest they do is to photocopy that. This is the rail, there's this. Then cut it off so the track is cut off and make your overlay. You don't have to have all three of them like I had over here. But just make an overhead, make your own overhead transparency. Because I think this is a nice way to show it with the wheels sloshing back and forth on the train. Oh my God, hey, is that what time it is? Our time's all gone.
I'm going to fill these bottles, or at least we'll start with one and see how far we get. I've got a pop bottle, as you can see, with just one hole. You don't need two. And if I take my thumb up here, guess what? Gravity never sleeps, right? The bottle is being held up, the water isn't. If we do a free fall demonstration with this, what should happen as the bottle is falling? Should the water still be leaking out? No. Because as the water is falling, whoa, I don't like this table, so is the bottle. So it's leaking out, leaking out, leaking out. As it falls, not leaking out. Because everything's falling together. Now, very hard sometimes for your students to grasp that anything that's up in the air is in free fall. When it's falling free fall makes sense. But what if I were to throw this thing up in the air? What would happen to the water in the bottle as it's going up? After it leaves my hand, it's going up in the air and then coming down. What's the water going to do on the way up? What's the water going to do on the way down? Check your neighbor and predict. Yes. Any ideas? What about coming down? What's the water going to do in the bottle? It's going to stay in the bottle. We saw that, didn't we? What about on the way up? Stay in the bottle. Stay in the bottle. How come? It's in free fall. It's going up, but it's falling down. Because gravity is always pulling down. If you watch carefully, you'll see that. Ready? The opening is where my thumb is. Okay, Susan? Opening's where my thumb is. I'm going to toss it in the air and catch it on the way down. You see that again? In slow motion.
Can't be done.
There you go. It only starts to leak when it comes down. Now, when we talk to our students about projectile motion, we tell them that all the time that the projectile is moving horizontally, it's doing what?
Free fall.
It's in free fall. So if Jennifer was to go way across the other side here with
The bucket.
the bucket,
I was going to insist on the bucket.
and I will be the launcher. Okay, what we're going to try to do is to maintain the bottle's attitude in the air, although it shouldn't make any difference. But if it starts to spin, then we've got another force at work here, which is not just gravity. So we're going to try to get it in the bucket first shot and watch to see what the water does as we go over. Are you ready? 3, 2, 1. Excellent. Good catch. Well done, Jennifer. Thank you. And the hole is still there. Okay? So this is one that you can do with your kids. You have your kids do it outside with the big 2-liter pop bottles. All kinds of fun. Get a nice day in the spring or the fall, and they can do projectile motion, free fall all the way across. As long as they're convinced that free fall is a condition for the water not to leak out. So you build on that, and then you can extend it.